Okay, this talk's a couple years old. I haven't given it in a while, but I really like the pictures in it. And there's an animation in Keynote that I worked very, very hard at late in the talk. It's possible that we'll watch it twice when I get there. It could happen. All right, it's about object-oriented design. And really, it starts out like this. This is a story. You love your life. You love Ruby, maybe you love Rails, you love your app. Everyone thinks you're a genius, right? You wrote the most amazing application, and then somebody asks for a change. Okay, so you crack open the code, you go look in your editor, you make a few changes, maybe you make a few more changes than you thought you'd have to make. You write a test or two, maybe you have to change some existing tests, but you check it all in, you put it in production, it works. Still a genius, right? And then, of course, they see it, and the first thing they do is ask for another change. That's not really what they wanted. They wanted something else, and they know once they see it, right? And so you're like, OK, I'll do that. You go, you crack open the code, you get the code, you make a bunch of changes, you make more changes, and it's maybe a little harder than it feels like it ought to be, but you get it done. You check it back in, you commit it, it's running in production. And then, of course, they like you, right, because you're successful, so they ask for a brand new feature. And you go look at the code, and you realize it was not meant to do that. Was absolutely not meant to do that. And so you're in this situation where, there's enormous pressure to get it done, and everyone's hair's on fire. And so you just start throwing in crap. You make change after change after change. It wasn't designed to do this, and you don't know how to fix it. And in the end, you just sort of hope there's some way you can avoid get blame. You just check the code in, make it work, and it's done, right? And so what happens is you wake up one day and you realize that an application that you once loved, now you hate. You hate Ruby, you hate Rails, you hate your job, and you hate your life. And this is really common. You are not unique in this, right? Oh, there we go. So this is what happens, right? Here, I have this and you do not, so I can point at that spot, right? The beta gets released and you're in love, and everything goes downhill after that. You were fast, now you're slow. You were happy, now you're sad. You were cost-effective, and now you're a money pit. Do you know money pit? You're a waste of money, right? Okay. All right. So the app is amazing. It started out amazing, and now it's a mess. And it doesn't mean that this is time to look for a new job. All right? Because that happens next. Amnesia doesn't help. Unless you change something, every app you ever work on is going to end up looking just like this. These applications are prisoners of their designs, and they've taken you hostage. You can't outrun this problem. What you have to do is you have to behave differently. You have to write a different kind of code. And what that means is you have to learn to understand the mess. Now, the problem with messes is, of course, that they are messy. By definition, right? They're hard to understand. Everything in a mess, everything in your code base is tangled up together. It's like a big tapestry, right? There's a warp and a weft, and these things are all wound together. You can't reach in here and pull on any thread without bringing a bunch of other stuff with you. That's exactly how your code looks. It turns out once you start making changes, you might think your app is decoupled, but once you start making changes, what you find is that everything you pull brings something else with it. And it turns out that your app is not this sweet little scene with furry little animals. No. Your app is trying to kill you. All right, and so when things are so coupled together, things get coupled together because of knowledge. Your app's made up of objects, and objects know things about one another. They always know things about themselves. Sometimes they know stuff about other objects, and it's knowledge of other objects that binds things together. So when an object knows something outside of itself from some other objects, that's a dependency. And you know what a dependency is, right? A dependency is something that if it changes, you might change it. Oh, I forgot about the balcony. Here, I'll look at you guys too. If it changes, you might change. Did they get exiled to up there? Were you bad? Sorry, here. It's been a long day, and I'm in the wrong time zone. So dependencies, right? They're things that you depend on. If they change, the consequences flow down to you. Now, you cannot avoid dependencies. Objects have to collaborate, which means they have to talk to each other, which means they have to know about each other. However, there are many different ways to solve most programming problems, and it's really easy to arrange your dependencies so that things turn out badly. I love my pictures. You can laugh, just laugh, that's fine with me. I tell you, I love this talk. I haven't given it in a long time. So if you want to manage dependencies, you have to understand about stability of code. So you have to understand the relative stability of the varying parts of your app. And there's a continuum of stability, right, that goes from wildly unstable code that changes all the time, all the way over on the other end of that continuum to code that's never changes, that almost never gets touched. And it turns out when you're trying to deal with dependencies that it doesn't actually matter about the actual stability of any piece of code. What you care about is that the things you depend on are just more stable than you are. Right? That's all that matters. And so there's situations where things that seem wildly unstable from some points of view can be perfectly stable from others. And it's just a matter of knowing that, of sorting out the relative dependencies, the relative stability. But the problem is with OO, well, with all languages, actually, I totally agree with just about everything Mario said. Where'd he go? Yeah. Let's clap again for him. He gave that a nice talk. Yeah, you're welcome. And so sometimes you're more like this. I know, who did that to that poor child? Like you're confused. And we're confused all the time about code. I write code that confuses me. And the thing that we're confused about is how relatively stable things are going to be. It's really easy to write code in the present where you won't know until in the future whether it's going to have to change or not. And this is where we need object-oriented design. Because it gives us hope. It gives us hope. You know, I confessed today in my class, I now have a dog. I never had a dog. I have a dog now. And so now I'm one of those people who's that way about their dog. And I realized when I was rehearsing this talk that I could have put a picture of my dog right there. Next time. I will. Next time. Okay. So this is object-oriented design will give you hope. It gives you hope. It can teach you how to separate the things that are stable from the things that are unstable. And it will show you how to depend on one and hide from the other. And if you can do that, it's going to dramatically improve your code. It gives you a way to manage the mess so that you can write apps that look like this, where the design stays high over time and you don't hate yourself in your job. It's object-oriented design that lets you stop worrying and learn to love the mess. All right, now we're going to look at code. I have 3 examples. They're all in Ruby. The Ruby code is easy to follow. So even if you don't have Ruby, you'll be fine. There's the 3 parts of the example. In the first one, I'm just going to put some code up, and I'm going to put a surprisingly simple code example up. And we're going to realize that there's an amazing number of dependencies, even in a small amount of code. And I'm going to give all those dependencies names. Then I'm going to change it. I'm going to do some things to make it more complicated. And then we're going to use principles of object-oriented design to isolate the instability and to manage the mess. In between every example, I'm going to jump up to like 10,000 feet, and we're going to have a little talk about what it all means. And so there's, I don't know, I've gone 7 minutes. I'm right on schedule right now. It'll be another 10 minutes an example or so. So you're going to be stuck there for almost 30 more minutes. 25 probably. All right, so get emotionally prepared for that. All right, here's example number 1. This is a game where, surprisingly enough, it involves bicycles. It's a game where people race bikes and they have to buy parts for their bike. One of the parts that you can buy is a shock. And so game knows game has implemented the shock cost method. It knows the name of the shock. It sends costs to an instance of shock. Shock implements costs with a bunch of lines of messy math, which I didn't even bother to write down. Right? It's a big, ugly, hairy thing that's many pounds of code right there. Now, the code in this block, the code here has these 2 qualities, 2 special qualities, right? It has no dependencies, which means nothing depends on it. Nothing depends on the internal implementation. And it has no dependence. Nothing depends on the internal implementation. And it also has no dependencies. It doesn't, nothing, and what that means really in English is that there's nothing you can change in the outside app that will force you to change this code. And there's nothing you can change in that code that will force you to change something in the outside app. Right? So no dependence and no dependencies. Now, this is a huge mess. But because it has those qualities of no dependence and no dependencies, I'm going to give it a name, a special kind of name just for this kind of mess. I'm going to call it an omega mess. All right? And here's the definition of omega mess. It's a mess that's at the end of the line. That's what it means to have no dependence and no dependencies. And so because it's, well, okay, let me do this first. it's still a mess, regardless of the fact that it has those qualities. And as programmers, I know that when you look at that code, you have a really hard time walking away from it. Tell me it's not true. I know you, right? And so one of the questions we face at this point is, should we fix that mess? Does it make sense for me to go and spend one moment of time trying to clean up that mess? Now, I have some suggestions about how to decide. Well, and actually, a thing I forgot to tell you before, and I always forget to say it in this talk, is that not only is the shock code a mess, but more shocks are coming. And we know that for a fact. They've already told us that. That is not speculative. I don't know what new shocks are coming, and I don't know what their shock calculations are going to be, but I am aware that new shocks are going to appear. And so given that, there's a real temptation on our part to do something to clean up that mess right now. And so I'm going to put that question in your head and then come back to it in a second. All right? Should I do something about it? What I want to do next is show you a different kind of view of that code. This is a sequence diagram, and it is, I'm sorry, UML. Yeah, exactly. Make that noise. Now, I have a really hard time with UML just because I can't remember all this stuff. Like, every time I have to draw a class diagram, I have to look it up, how to, like, what points where. But I love sequence diagrams. Sequence diagrams let me, in my brain, this is what code looks like. And it's really nice to have a way to express objects and the messages that pass between them without having to write code. And so if you've never seen a sequence diagram, here's how they work. There's boxes, they repeat at the bottom. These represent objects. There's a little dashed line to connect the two boxes that are the same. The shock cost message being sent from player to game is denoted by that dark line that you can tell the receiver of a message because it has the filled-in arrow. This gray vertical bar expresses the fact that game is busy in that method, and then the return coming back to player is that. All right. And I used these guys. Every sequence diagram I did, I drew from this website. I took their name off the other ones, but I just want to make sure you see that I gave them credit. All right. So this picture is a visual representation of the code that you just saw. And I'm going to mark it up a little bit with two things, right? I'm going to draw arrows on it that indicate knowledge, and I'm going to color code those arrows for stability. So if I know something about another object, I'm going to draw a solid line. If I know something in myself, an object knows something about itself, I'm going to draw this dash line. I'm going to color code stability with things that are highly unstable are going to be red up to green, which are things that are super stable. And so let's look at this. So game knows the name of the shock class. It knows that the shock class responds to the new message. It knows that the thing that comes back from new responds to cost. It knows that instances of shock implement cost. Shock knows that it implements the cost message, and it knows its internal implementation in that method. And that's a bunch of stuff for not much code. And you can also tell here that everything shock knows is about itself, but game knows an awful lot about shock. If I were to draw that picture a different way, I would draw it like this. Shock doesn't have any dependencies, but game is a little stuck to shock. This is a problem with the tapestry, right? I can test shock in isolation without game coming along, but if I'm going to test game, shock's coming with it. This is where you get in that stubbing and mocking and stubbing and stubs, right? Because I'm sending new to it here. And so this can be a mess. This is what makes code entangled. I can use shock independently, but I cannot use game. Game is bound to shock. And so I think one reason why I like this sequence diagram instead of the code is in the code, there could be huge amounts of code in that cost method, and we tend to evaluate the importance of things by the pounds of code, right? The amount of code in the cost method could overwhelm all the rest of the stuff in the class, but really, it's just that important. It really means nothing, right? That's a mega mess. It's hidden behind the message. So as long as it's there, I don't have to think about it. From outside of shock, all you have to know is that I can send the message. And so we can think of these messes as being hidden behind the messages that we're going to send. Now, this view of reality, like I said, is a little deceiving because the amount of headspace, however much code this is, takes up a lot of room. But don't be misled. It's not about this code. It's about the message that we want to send. All right, so now you've seen a little bit of code. I'm only slightly behind time. Let's take a little break and think about this from a higher level. So think of this as a plot. It's a space where I can put a marker for every piece of knowledge. And here's how it works. The horizontal axis represents stability. Things that are really stable will be on the left. Things that are really unstable will be on the right. The vertical axis represents whose responsibility it is. So if it's my job, if it's my responsibility, it goes on the top. If it's somebody else's responsibility, it goes on the bottom. So in the upper left quadrant, things that are your responsibility and that are stable should be part of your public API. And what you do with that code is you share it. You expose it to other people. On the upper right-hand quadrant, the things that are unstable but that are your responsibility are private behavior, and it should be contained within your object, but you should hide it. Other people shouldn't be able to get to that. Everything below the line is a dependency that belongs to somebody else. And if it's a stable external dependency, like you're sending a message in somebody else's public API, you can have those, but you should minimize them. The problem is the bottom right-hand quadrant, right? Unstable external references don't belong in your class, and those are the things that make code hard to change. That's why everything changes every time you touch something. And so if we take this, we take the shock knows the name of the cost method and the cost calculation, and game depends on the existence of the cost message, the name of the shock class, and the receiver of the cost message. We can take each one of these bits of knowledge and put it somewhere in that quadrant, and it can help us make decisions about what we should do with code. And so let's take the first one. Here's the cost method. Cost is part of the public API of shock. It belongs up there. I should expose that, which is what we do right now. The cost calculation, it's a private. Those internal implementation details are private to shock. They belong in shock. They're over in the right-hand quadrant. I shouldn't let other people in on that data. They must get to it via the public API. The fact that the game depends on the cost message, that is an external dependency, but it's a dependency on the public part, the stable public part of someone else's API, so it belongs over here. I'm allowed to know that. You have to know things about other objects or you can't collaborate, right? And so that's perfectly okay to know that. The problem comes when we start looking at these things, knowing about the shock class and knowing that who receives the cost method, the message. And the problem right now, it is entirely likely, if you're writing this code, that you do not know about the relative stability of those things. This is the baby in the snowbank part of your code, right? It could be here. It could go anywhere along the continuum, and you cannot decide in the present. That is information that you'll get in the future. So we don't know what to do about that. And so I asked you a while ago, I'm going to come back to that too. All right, we're going to make a decision about that. I asked you a while ago, before we left this code, if we should do something about this mess, if it was worthwhile, cost-effective for us as programmers to do anything about that mess. And there's a lot of uncertainty around this, right? I've confessed to that. Design, at this point, there's a very simple thing that you can ask yourself that will help you be guided, let your design be guided, and it's this question. What is the future cost of doing nothing now? It is very often true that whatever change I would make in there would cost the exact same later as it does today. When the future cost of doing nothing now is the same as it is now, you should wait. I don't care that the code is ugly. I have no sympathy. I have no sympathy with your annoyance about that ugly code, all right? Kent Beck famously said, "You'll never know less than you know right now." And that's an absolute fact. You will never know less than you know right now. There's no change that you can make in there that you cannot, that I can't suggest an alternative requirements change in the future that would make your change incorrect. You should wait for more information if the future cost is the same as the present cost. Now, having said that, I would probably make a change or two. All right? Here's what I would do. I would inject this dependency. I would probably break, if this is a big, long method, I would probably break it up and give parts of it names. But it is fine with me if you do not. I don't think of these changes as design. These are not design. These are neatening. This is like the last scanning of an email to make sure that you don't have any typos in it before you send it. Right? I'm trying to communicate with future readers by giving people good names. I do these things almost without exception because doing a refactoring that neatens code is like buying a ticket in a lottery that's rigged in my favor. Those things pay off so often that it's worth doing them every chance I get. but I don't think of them as design, right? It is really just a neatening kind of thing. And so, but for now, we're going to leave that code just like it is. I'm going to now make a change in requirements. So, of course, the game's a big success, and now they want stuff from you. They want you to do more things. And what they want is new shocks that vary in cost. And some programmer has already implemented this. And here's what they did. They went a game, and they injected a variable called type into the shock cost method. And then they changed the new method in shock to take type as an argument. All right, that's not so bad so far, but now let's look at what they did over there in cost. So they saved it. They had saved that piece of state. And then they did this. All right, now, it used to be, so now in this code, there's not one calculation, but 4. And I know all the types. And I know the different parts that go with which one. And so if I look at the sequence diagram, the sequence diagram actually doesn't look that much worse. But the problem is you cannot tell you can't tell except for the conditional part that's put there. You can't tell that something really bad just happened. And the question I have now is the case statement in there, is this still an omega mess? I could leave the mess when it had no dependents and no dependencies. But now that someone has gone in there and put that conditional, think about it for a minute. Are there dependents on that mess? Is there anything outside in the app that could change that would force me to go in and change that code? It didn't used to be true, but it sure enough is true now. Let's make a list of what we know, right? I knew the name of the cost method and the calculation itself. One hasn't changed, but look what happened here. Now I know 4 different shock cost calculations, and I know the symbols for the types, and I know which type goes with what calculation. And if anybody in the app makes a new type, I have to change this method. All of a sudden, I'm vulnerable to changes in distant places. And if they change in distant places, it's possible that I'll forget to make a change here and code will break. This is a thread I don't want anybody to pull on. So that's not an omega mess anymore. It's actually, I'm going to give this a different name, which I hope is on the next slide here. Let me look at my notes. Yeah, here. Oh, sorry. It's not a mega mess. It's something I call meta-knowledge. And so meta-knowledge is, if you think of an omega mess as being contained inside a piece of the puzzle, meta-knowledge is about how the puzzles fit together. It makes this big piece. It takes meta-knowledge to assemble all your objects together, which is now what's in that method. So in a minute, in example number 3, we're going to fix that. But before we go there, I want to go back here and put all this knowledge on that plot. All right, so we already know the cost method doesn't change. I'm not going to worry about that. But what about 4 shock cost calculations? When I had 1, it was an implementation of a private method that lived in this class. But now that there's 4, the knowledge that there's 4, that's what it used to be up there. But what happened is it's unstable and it moved down there. It's not my job anymore to know those things. The same is true for the fact that there's 4 types. It's a very similar kind of thing. It goes down in that quadrant. It oughtn't be me that knows that stuff. It's not about shock. And then finally, the mapping between which type gets what calculation. This is probably more stable than the other 2. It's unlikely that the mappings would change, but it's at best, I can put it over there, all right? And so now, it's these dependencies that make code not only costly to change, but likely to change. Once you get 4-ness, you can bet that 5-ness is not far away. Like, we know that's going to happen. While I'm coupled to these things, the costs are going to be high. And it was the case statement, adding that case statement, that ruined a perfectly good omega mess. Now, it's really unfortunate because it's easy to avoid these dependencies. And here's the guiding principle. I would rather send a message than implement behavior. I don't want to know stuff. I just want to know people who know stuff, other objects that know stuff. Now, I know that seems like I'm just kicking the can down the road, right? But it's a can that we want to kick, right? Now here, it's interesting here, I want to send a message instead of doing those things, but the problem is, who's the object? Where am I going to send it? I don't have an object to which to send the message. And this whole problem with the case statement occurred because somebody got tasked to make a change and they went and found code like it and they put more there. And you know you do that, right? What they said was, this is the question they asked themselves. In what object should I put this code? And that's what leads to this stuff. You put more where stuff like it is. The question you should ask yourself instead is, what message should I send? And then, if you find the message, you can just make up a new object to receive it. And I know that might seem shocking to some of you, right? I'm going to make new objects because I care about messages. And then I'll figure out what message I want to use. I'll make an object if I have to, and I'll send the object to that message. And that brings us to example 3. The way you do this is something they call object-oriented composition. I could explain it, but it's just so much easier to show you the code. All right? So here's what we have. I got this. Notice there's my original mess. I'd rather send a message than implement behavior. So I just have to decide what message I'd like to send right there. And so maybe I'll call it compute, right? I want something to do that. And so now I need to create some obliging object, right? I need a receiver of that message. And it's super easy to do. I'll just take... I'm just going to take I'm going to make it a class name by combining all the bits of information I know and put the compute message in there and move the mess to there. Now notice what happened. I got my mega mess back. That's what's in there. And so now we have someone we can ask. I can just send the message, and you can do that to every one of these guys. You can take that. So now I'll send the message up there. I can just do it for that and all these. And I can hide them all. I can make a thing like that. I can make a thing like this. This is polymorphism. I'm making a bunch of objects that play a duck-type role that conform to the same API. Super easy to do, right? I really am just moving code around, and I'm making a bunch of little tiny objects, and that's a good thing. Don't be afraid of that. I had a little rant today with the group I'm teaching here about if you're a Rails programmer and you're afraid to have small objects because you perceive that you'll have a bunch of files on disk, you should go read about the require statement. There's no reason why you can't I would put all these classes in a file together so I could look at them all at one time. And then you end up with this marvelous code. I'm sorry. It makes me laugh. Because the reaction I always get is like, really? This is better? This is why people hate design, right? They go just to this point. And it seems as if, this is what people tell me when they look at this. They're like, great, you hit all the code. Now you made a bunch of new little objects that are somewhere I can't find. And you copied I used to be able to look at this method and tell what it did, and now I have no idea. Right? And you can't really blame them, actually, for that. But let's talk about, some things are better, even with this variant. Even with this variant, some things are better. And let's be real clear about what they are. Shock used to know 4 shock cost calculations, and now it doesn't know that anymore. It knows the names of 4 classes. And it used to know what type went with what class, and now it used to know what type went with what calculation, and now it knows what type went with what class. And this is there is definitely an improvement in code here if you can tolerate not knowing what things do, if you can just trust them to behave correctly. Because the calculations have now been isolated. I have a bunch of Omega messes now that are independent of change to the rest of your app. Now, but the bad news is I still have a whole ton of dependencies. All right? I just traded the dependency I'll know in the implementation for the dependency I'll know in the name of the class. And if you add or remove shock, you still have to change this method. All right? So while some things have improved there, it feels like we didn't really reach the holy grail here. And I really hate that. In the language that we've been using, in the language that Mario used, did you talk about open closed? You did not. He did not. Okay, sorry. So he mentioned the S in solid, the I in solid, the L in solid, even though he said he couldn't do anything about it, and the D in solid. And the missing letter is O, which stands for open closed. This is what they would call closed for modification, which means you can't get new behavior out of it without going in here and editing the code. And I would like it to be open for modification. I would like it to work even if other things change. And it's really easy to do that if you can bear to do a little metaprogramming. Shall we? So notice there's a convention here. When the type is the prefix for a class name that ends in shock cost. And so knowing that, you could use that, just like Rails, you could use a convention to configure this by saying something like this. You could generate the string class name like that, and then you could eval it, and that turns into the class. Now, everybody who knows Ruby is like doing this to me right now, because that is really the worst possible way to do it. But I do like to see the looks on their face when I do that. Okay, and there's other ways to do this. You could do that. Once I can dynamically build the class name, there's a whole bunch of ways. If I can get a string that looks like the class name, there's all kinds of things I can do in Ruby to turn it into the actual class. So I can eval it. You shouldn't do that. I probably shouldn't even put it on the slide. You can look it up in the big hash in the sky where Ruby objects get defined, where constants get defined. You can do that. If you're a Rails programmer, they've already monkey patched string for you in advance, and they've got constantize. And all that does basically is this. It looks it up in the big constants hash in the sky. So this is a tiny bit. If I know any of these techniques, I can use them to create a tiny bit of metaprogramming, which is actually 2 lines of code only because it would not fit on one slide, right? It's really 1 line of code. And I can use this to manufacture, a word I use very advisedly. I can manufacture an instance of the right class. And I say manufacture here because this is a factory. And I know that here's how we feel about factories. We love them. And we love factories because we want to do object-oriented programming. We want to create many duck-typed objects that polymorphically play the same role. And so our problem switches from knowing the reason we might switch to knowing all the things that we would do when we switch, that big case statement with all the behavior in it, to having to pick the right class. And that often involves a factory. It's as simple as that. And so now that I have the factory, I can get rid of that whole case statement. I don't need to know that. I don't need to know any of those things. I just need to know the convention. If you follow the convention, I can manufacture an instance of the right class. And if you create a new object, if you follow that, if you create a new object, you get a new type, you make a class, it'll just work. My factory will manufacture it. And so here's the code we had before. It looked like this. And then after we got this, and you notice here, it's interesting. Everything I just whited out has to do with picking the object. And so I would probably pull that into a method of its own. I would make a little method that just created the new object, and then you could do that. And at this point, probably the next refactoring, it's easy to imagine a refactoring where you want this to be reachable for other parts of your system. Maybe other people need to access the factory. When that happened, you would just move this someplace out, put it someplace accessible from the system roots, put it in a class or wherever makes sense to you. And so now, there's almost nothing you can do in your application. The only thing you could do in your application that would cause you to edit this code would be if you changed the convention, in which case everything is broken anyway. So this is a huge win, right? You can make all these, you can make more of them. Kids can come into your shop that have no idea what you're doing and make more, and it will work. Right? If they get the convention right, that's all they need to know, the convention to do things. It's a huge win. All right, now I have the animation that I forewarned you about, right? Because here's the problem. Like in my brain, you may be different. I mean, everyone is. Code is a weak, feeble, gray reflection of how programs look in my head. Code requires a lot of interpretation and reimagining from me. This, to me, I'm going to show you, this is what composition feels like to me. I had the shot class. It knew one thing, and then I put 4 things in a box. And I don't want to have a conditional in that box to pick them. So what I did is I pulled all the stuff out, and I wrapped them in classes, and then I picked an API. I picked a polymorphic API, and I let everything implement, all the new guys implement it, and Shot can now send it. If I do that, then I've hidden all the implementation details behind the message. I don't care what's back there. I don't know the names of those classes. I don't know what they do. I'm perfectly okay with that. They respond to compute. It just works. And if I want to make a new one, all I have to do is conform to the same API. This is the definition of a role. Shock's cost method doesn't know or care the class of the object to which it's sending the message. The factory generates something it doesn't know its type. It just expects every collaborator to play the right role. And so when you think of your collaborators as a kind of the role they play, rather than as a type of the class they are, you end up in this situation where you're dealing with duck types. You're having a conversation with duck types, which means you can plug them in and change them behind the message, and nothing about the rest of your code will break. When you can manufacture the right thing and trust it to play the role that you expect, you can just send the message and everything gets easier. You end up with applications that are built of pluggable Lego-like parts that you can interchange for new things. So that's it. Find the message, make the object, send the message. We don't have messages. We don't send messages because we have objects. We have objects because we send messages. It's Alan Kay has said later in life that he wished he'd called it message-oriented programming. It's not about objects, it's about messages. So, there you go. It does not matter to me. I am, Internet Sandy on the internet, and I talk to people a lot about how to write good code. And I do not care if you make a mess. I don't care. Most of the messes you have, it is not cost-effective to clean up. It is not necessary to clean them up. That your business doesn't need you to clean them up, and you shouldn't indulge yourself, right? If there are mega messes, just hide them. Right? If they never change, especially in a mega mess, it never changes. Like, don't voluntarily go touch code. When you do that, if you go to a mega mess that hasn't changed and you voluntarily change it, you voluntarily spend time editing it, you're telling your business, making this code look better for me is more important than anything that's on the backlog. That's what you're saying. There's an opportunity cost for change, and time is a precious resource. We have to really spend it carefully. So all I want you to do is recognize when you have meta-knowledge and organize it so that you can hide it behind stable interfaces. All right, so I know a moderate amount about object-oriented design, and a lot of it I learned because I was ignorant and I wasn't aware of the literature, and I made a bunch of mistakes and had to figure things out myself. I walked into the headwind. And it was fun, right? Like I got better at it. I wouldn't say good at it, but I learned a lot from making mistakes. But when I look back on the sum of the suffering that I endured, it was pointless and a waste of time. There's a huge amount of literature out there. Granted, some of it's hard to read, but there's a few things that if you're writing OO, you should go read some of the classic books, maybe get a friend and make a book club, because all the things I've talked about today are really, they're available for you to learn. And you should do that, right? You do not have to reinvent this wheel. It could be that you're special, but I doubt it. All right? Like, don't make up everything yourself. So here's what object-oriented design says. It says dependent stability. Stability is relative. You should notice it and depend on things that are more stable than you. It says that what you want is more stable than what they do. And that's why you depend on the message. What you want is more stable than what they do. It also says that reality is messy and uncertain and changeable, but from the outside, from where I stand, I do not care what's in that house. You can make any change that you want in there and it will not affect my code. Just hide it. Just absolutely hide the mess. So, as I was saying, we stand on the shoulders of giants. It's a really amazing thing. Like, I am old enough, okay, I'm going to confess, I am old enough so that I wrote a lot of code before we had the internet. I know, scary, isn't it? Because I'm a woman of a certain age. And so it is amazing to me now that we live in an age where the best thoughts of anyone are available to everyone. You can easily find good help about how to write code. And you don't have to be a genius. I have the best pictures here. Like you can start off right there, right? That little tiny weeks old looking to me baby in design. But there's plenty of help in the community. Like you can grow and learn and look stuff up, and it doesn't necessarily, it won't always be easy. There's no guarantee that you'll be happy every step of the way. But if you do that, if you persevere, if you just look around and talk to other people and take advantage of the information that's out there, a time will come when you can write applications that bring you nothing but joy. Because you can never outgrow the principles of design. They'll let you, if you learn them and listen to them, they'll allow you to write applications that you'll love forever. Thank you.